The two greatest leaps of 20th century physics still leave physicists grappling to understand how it's possible, at a fundamental level, that they can coexist. On the one hand, we have Einstein's general theory of relativity, which treats space as a continuous, smooth background that's deformed, distorted, and compelled to flow and evolve by the presence of all the matter and energy within it, while simultaneously determining the motion of all matter and energy within it via the curvature of that background. On the other hand, there's quantum physics, governed at a fundamental level by quantum field theory. All the quantum weirdness is encoded in that description, including ideas like quantum uncertainty, the superposition of states, and quantum indeterminism, fundamentally anti-classical notions. Traditionally, approaches to unify the two have focused on quantizing gravity, attempting to place it on the same footing as the other quantum forces. But a series of new papers led by Jonathan Oppenheim takes a very different approach, creating a post-quantum theory of classical gravity. Imagine a world where gravity isn't forced to fit into the quantum mold. Instead, this post-quantum theory suggests that gravity could remain classical, coexisting with quantum mechanics without the need for quantization. It's often said that general relativity and quantum field theory are incompatible, but it's difficult for many to understand why. After all, for problems only concerned with gravity, using GR alone is perfectly sufficient. And for problems that are only concerned with quantum behaviors, using QFT alone, which normally assumes a flat background for spacetime, is perfectly sufficient. You might worry that the only problems would occur when considering quantum behaviors in regions of space where spacetime is more severely curved. Even in those regimes, you might intuit a way out. Why, for example, couldn't you have space, or spacetime, always obey the laws of GR and then have all your quantum particles and fields exist within that spacetime, where they obey the quantum laws given by QFT? That's the approach that many have taken, including Stephen Hawking, which is how he derived the infamous effect of Hawking radiation, by calculating how quantum fields behaved in the severely curved, classical spacetime outside of a black hole's event horizon. Known as semi-classical gravity, this approach is valid in many regimes, but it still doesn't take you everywhere. It doesn't tell you what happens at or very close to singularities, where general relativity breaks down and gives answers that make no sense. It doesn't explain what occurs when you encounter quantum fluctuations on the smallest of scales, below the Planck scale, for example, where every fluctuation should be so energetic on such tiny scales that a black hole should eventually form. And it doesn't describe how gravity behaves for systems that are inherently quantum in nature. That last one is extremely important, because while we lack the technology to get very close to singularities or probe sub-Planckian scales, we deal with inherently quantum systems, including ones made out of massive gravitating particles, all the time. Consider, for example, a double-slit experiment, where individual particles, even one at a time, are fired at two very narrow, closely spaced slits. If you measure which slit each particle goes through, it will wind up in one of two locations, one corresponding to a path where it goes through slit #1, and another corresponding to a path where it goes through slit #2. If you don't measure which slit each particle goes through, it behaves as though it passes through both slits simultaneously, interfering with itself in the process, and landing in a location described probabilistically by a wave function on the other side. This works for photons, electrons, or heavier composite particles too. This behavior, within the double-slit experiment, is right at the heart of quantum mechanics. But now let's ask a slightly deeper question. What about gravity? What happens to the gravitational field of a massive particle as it travels through a double slit? If you measure which slit the particle travels through, the answer is easy to intuit. The particle's gravitational field just corresponds to wherever it was at any point along its trajectory, as it passed through the slit and onto the screen behind it. But what if you don't measure which slit the particle goes through? This is a big challenge because with plain old GR and QFT alone, we don't get an answer. Does the gravitational field split, interfere with itself, and curve space the way you'd expect a quantum mechanical entity to? As though it were distributed in a probabilistic wave-like distribution across a wide range of spatial locations. That would be an indication that gravity is inherently quantum in nature. On the other hand, if it simply followed a well-defined classical trajectory, that would be an indication that not only isn't gravity inherently quantum, but it would have tremendous implications for how we conceive of the behavior of particles, as it might provide evidence for some sort of hidden determinism buried deep within quantum physics. Which one is it that will occur then when it comes to gravity? This idea was first explored in a paper by Don Page and C.D. Geilker, all the way back in 1981, who cooked up a thought experiment involving a radioactive lead mass in a superposition of states, a Geiger counter that would cause the quantum system to decohere, or collapse the wave function if you prefer, and a test mass that would gravitate. If the test mass gravitates towards either of the two possible final state locations that it's in a superposition of, as shown at left, that would indicate that quantum mechanics is purely a statistical effect, and that massive enough particles have determinate positions and gravitate accordingly. If the test particle instead falls down the middle, as shown at right, that indicates that the semi-classical prediction is what occurs. The average trajectory taken by the test mass is what determines the gravitational effects of the particle. If enough time is allowed to pass before the entanglement is broken, or the superposition of states decoheres, a high-quality experiment should be able to tell the left-hand case from the right-hand case, and should teach us whether gravity is at least partly quantum, for the case at right, or whether gravity is deterministic all the way through, corresponding to the case at left. Unfortunately, this is not an experiment that we know how to perform just yet. It's a thought experiment only. Imagine conducting a thought experiment similar to the one we discussed earlier. This time, consider a particle passing through a double slit, creating an interference pattern on a screen. Despite the particle's uncertain position, it can still have a well-defined and highly precise momentum. The fascinating part is this. If the particle's gravitational field is classical, you could measure it with enough precision to determine the particle's position without disturbing it. This would reveal which slit the particle passed through, potentially preventing the particle from being in a superposition. This scenario could challenge the uncertainty principle, which states that you cannot know both the position and momentum of a particle to arbitrary precision. But what if the classical gravitational field doesn't respond deterministically to the quantum system? What if it reacts in an indeterministic way? This brings us to a groundbreaking idea proposed by Oppenheim and his students. They suggest that the gravitational degrees of freedom might only contain partial information about the particle's location. This idea introduces the concept of stochasticity, where random processes inherent to quantum systems also influence classical quantum dynamics. Consider the implications of this for the black hole information paradox. This paradox revolves around the information contained in particles that form a black hole. Over time, black holes emit Hawking radiation and decay. The big question is whether the information is somehow encoded in the outgoing radiation, or if it is destroyed, challenging the principle of information conservation. What if the universe is fully deterministic? If so, gravity as we understand it might break down at low energies. Conversely, if gravity is semi-classical, a pure quantum state, where information is preserved, could evolve into a mixed state, where information is lost. This brings us to the persistent information loss paradox. None of the attempts to resolve this paradox have been theories of gravity. A recurring issue is backreaction. When quantum scale events influence spacetime, how do those spacetime changes then influence quantum scales in return? This is the crux of a new set of papers that don't shy away from the complexities and potential issues inherent in new theories. Whenever a radical idea is proposed, it's usual to encounter pathologies, incompletenesses, and outright failures. These aren't deal-breakers, but rather stepping stones. Consider Alan Guth's initial paper on inflation, which was fraught with problems, yet sparked a revolution in cosmology. The early attempts at quantum theories by pioneers like Bohr and Schrödinger also faced significant issues. The first quantum electrodynamics formulations were riddled with mathematical inconsistencies. A new theory must clear 3 hurdles to supplant the old model, reproduce the old model's successes, explain problems the old model cannot, and make new testable predictions. We're far from this final stage with postquantum gravity, but it's crucial not to dismiss new ideas prematurely. Despite a knee-jerk reaction against this approach, it's worth exploring what happens when we abandon certain assumptions. Semi-classical gravity has its pathologies, but the post-quantum approach, where classical gravity couples with quantum field theories and modifies quantum mechanics' dynamical laws, shows promise. It tackles the measurement problem in quantum physics by introducing classical spacetime interactions with quantum degrees of freedom, causing decoherence in quantum systems. This hypothesis eliminates many quantum gravity problems by suggesting gravity might not be quantum at all.